Hello, this is Group A7. I'm Joe Mike Milley. Also in the group is Justin K. Putt and Chris Winfrey, and we'll be talking about finite probability space. So, first we're going to have to talk about the sample space. This is the set of all possible outcomes, normally denoted by a big S. For a coin, if you flip it once, your outcomes are either heads or tails. That's denoted here. What if you flip it twice? Then this would be your new sample space. And that's either you get a heads first and then a head second, or a heads first, a tail second, a tails first, a head second, or two tails. That's how that one works. If you have a dice, the possible outcomes are 1, 2, 3, 4, 5, and 6. And if you have a hand of cards, while I can't show you by example every single possibility, we do know the cardinality of that set, and that will be 52 choose 5, because you're choosing 5 cards out of a deck of 52. An event is a subset of the sample space. So now if we go back here and we look at this set, an event of a coin flip could be E heads, which would just be this, right? And if you're talking about when you were flipping the coin twice, say you wanted the event where you did not get the same result, which would be E diff, we'll call it that, and that would be heads tails and tails heads, because you did not want the same one to come twice. Exhibited here, one event is heads, which is a subset of S, which is heads and tails. That's one thing. The event is always a subset of the sample space, because if an event were not a subset of the sample space, then that would be the equivalent of rolling a dice with 1 through 6 and getting the number 8. That doesn't work. So 8 can never be an event in this situation, because 8 is not a subset of the sample space of a dice roll that only has 6 numbers. Now we're going to talk about finite probability. This is when we're dealing with a sample space that is finite. The probability distribution P is a function from the sample space to the set of real numbers, such that 0 is less than the chance of the event is less than 1. Key things to note: the chance has to be 0 or greater, and P of E is less than 1. This means that the probability can't be more than 1. This makes sense because that would be more than 100%. And this upper bound of 1 makes more sense when we look at the definition of P right here, which is the cardinality of E over the cardinality of S. If E is a subset of S, it cannot have more members than S does. And that is what would happen if P of E were greater than 1. That would mean E is greater than S. We define E to be a subset of S. Therefore, we know that these bounds hold. Other interesting things to note about this probability function: the sum of all the events must equal 1. So that must mean, that's essentially saying something happens. Something happens. Even if one of the things in your sample space was nothing happened, that nothing happened. It's kind of complicated, but essentially you just need to have a total of 100%, or else the world is undefined. We could also define, for a specific case, the uniform distribution. That means every element of S has an equal probability. So if the cardinality of S is n, then the probability of any particular event S in the subset of S is 1 over n. This makes sense. If you have a red ball, a blue ball, a yellow ball, and a green ball inside a box, that's a cardinality of 4, and the chances that you'll randomly pick either one of those is 1 over 4, and this does extrapolate to higher numbers. Here's an example problem using these facts that we just learned. A box has red, blue, yellow, and purple balls. we're given that the probability of a red ball is 1/9. The probability of a blue ball is twice the probability of a red ball. The probability of a yellow ball is 3 times the probability of getting a red ball. The probability of a yellow ball is 3 times the possibility of getting a red ball. What we're trying to figure out is what is the probability of getting a purple ball? We'll go to our notes. And what we see here is fairly simple. The probability of a red ball is 1/9. The probability then of a blue ball is 2 times the probability of a red ball. And the probability of the yellow ball is 3 times the probability of a red ball. What do we know? We know that it must equal 1. The probability of all these things must equal 1. Therefore, we could just do some arithmetic, and we say 1/9 plus 2/9. This is red. This is blue. Plus 3/9. This is yellow. Plus the probability of purple, we don't know this yet, is equal to 1. Simple arithmetic shows that 1 minus 6/9 is equal to the probability of P. So the probability of P is equal to 1/3. This is, of course, assuming that the only balls inside of this box are red, blue, yellow, and purple. Now we'll look at some equalities with this very basic finite probability function. The probability of the complement of E, so the complement of an event, so basically the chance the event does not happen, is 1 minus that of the event happening. Now let's think about that. Why is it that P of E bar equals 1 minus P of E? If we look at this, we can essentially see something very clear. If we treat 1 as P of S, because as we said, the sample space, the sum of all things in the sample space equals 1. And if you treat it like this, you get to see something like this. Right there, the complement is equal to S minus E. Given another very useful one is this equality right here. This is saying the union of 2 different events is equal to the first event, the probability of the first event, plus the probability of the second event, minus the probability that both of the events happen. If they're disjoint, however, we can ignore this term because we already know that E1 and E2, this set is the empty set. We know that because what we're saying is these 2 events do not happen at the same time. If they're disjoint, what we do have is the probability of the union of said events is equal to the union of the probability of said events. This is a special case for disjoint sets, and this once again intuitively makes sense because we're saying that there's no overlap. So essentially if there's no overlap, you're essentially just adding these, and however many unions you have, you're just going to be adding these, ignoring this term, which is just the syntax that's shown. Here's a fun problem using what we have just learned to solve a slightly more complicated problem. Say, what is the chance of a hand with all hearts? What is the chance that a hand has all hearts? So, we'll call this event EH for E heart. Now let's think about it. What is P of EH? How could we do that? We could do this in several ways. But we're going to use what we just learned, and we're going to say that over the total sample space. If we use this definition as a probability and walk ourselves over very quickly to the Notepad software. What we have here, that's fun. The probability, how many different hands, how many ways are there to get a hand of 5 hearts? That is very simple. That is 13 choose 5. Because there are 13 hearts and you're choosing 5 of them. The total, however, put that C there, is C of 52 choose 5. We do this simple calculation and we get, I have it written down here somewhere, it's 1287. That total probability is 33 over 66,640. That is the new way to do it. This is what we've just learned. We could have done it previously a different way, which of course would have been. And if you follow this path down and then you add the total from 5 hearts to 4, 3, 2, 1, and 0 hearts, you get 52 choose 5, which was the total number of hands. Why is this significant? Because any hand of 5 cards is either all hearts, 4 hearts, 3 hearts, 2 hearts, 1 heart, or 0 hearts. That's all the possibilities. So we want all those numbers to total the total amount of hands. And that's what we have here. And so this holds that the P of heart of I, the sum of all those, is equal to 1, which is very important.